Alright, so today we are going to be looking at operations on radical expressions. The last time we defined what a radical is, really it's any nth root or square root, or you can kind of think of it as any root of whatever number you're working with, or variable in this case. So you have these fancy root symbols that define what a radical is. The thing inside is called a radicand. And if you see a number up here, kind of in the little valley section, that is the index, okay? So one of the things that we need to do when we work with radical expressions is to make sure that they are in simplest form. So here's just a really simple example. I've got the square root of 32. The trick with these numbers, anytime you see something like this, is that you want to break whatever your radicand is, or whatever is inside of that radical, into what ideally would be perfect square roots, or perfect roots. So we know that in this case, if we break it apart, 16 is a perfect square root. 2 can't be broken down any further, so if you take the square root of 16, you get 4, and that 4 is going to multiply times whatever is remaining on the inside. Okay, so one of the properties that we deal with here is the product property, and what this is saying is that if we have the nth root of a times the nth root of b, we're going to get the nth root of a times b. So you can separate anything that's inside of a square root sign or a root sign as long as they both share the same index. And yeah, I mean, pretty much that's it. So you can essentially factor the inside and then work your way towards simplifying even more. All right, when we add and subtract radical expressions, we're going to use a lot of the distributive property. So let's take a look at a couple of examples here. The first one, if I have 3 times the square root of 5 plus 8 times the square root of 5, that is the same thing as 3 plus 8. So you can see the factors 3 and the factors 8 are added together, and that whole thing is multiplied times 5. So again, you can simplify by adding like terms. 8 plus 3 is going to be 11. Root 5 is going to be the guy that is multiplying here on the right-hand side. Similarly, we could do it with cube roots, or higher roots, higher indices. So in this case, because the items that are factored, cube root of 3x and cube root of 3x, are both in each piece, or term in this case, then I can do 2 minus 9. So 2 minus 9 times cube root of 3x is going to be a minus 7 times the cube root of 3x. Okay? So in other words, the radicand, the thing that's underneath your radical sign here, has to be exactly the same. Otherwise, it won't work. All right. When we do multiplication, it's again a similar idea. So say, for example, I've got 3 times the square root of 7, all raised to the second power. That 2, that exponent, is going to distribute to both of these items. So I would have the square root, or sorry, 3 squared times the square root of 7 squared. And this is what you get. 9 times square root of 7 times square root of 7, because 3 squared is 9. Square root of 7 is, I'm just literally multiplying it out. And then here, I combine them using this property up here, the one that we talked about above. Combine them underneath, I get the square root of 49, which is literally just going to be 7. So 9 times 7 is going to be 63. Here is another example. This is using radicals with variables underneath them. So you can merge them together, then you can split them apart in a way that would work to your advantage. In this case, because I've got 4x squared, that actually is itself a perfect square. X times x is going to be x squared. 2 times 2 is going to be 4. That means that I have a 2x right there. Okay? Dividing radicals, I'll go through a couple of examples here, but long story short, you can take, if you do the, similar to what we had above, when you do the radicals and you multiply, you can combine them together. It's the same idea. You can take the radical with the index pulled out and then divide through by a fraction. But when we're finding things in simplest form and you're working with fractions, sometimes there's a little trick that you have to do to fix it. If you have just a straight radical in the denominator, you'll just multiply. It's almost like finding common denominators in a way. You cannot have radicals in a denominator. So I'll go through some examples here. Hopefully this will all make sense. And in the meantime, let's just go ahead and switch over to the board. And let me... All right, let's see here. Hang on just a second. I got to sort my camera out here. All right, there we go. So let's go ahead and switch to the board. I've got a few problems. Let's go ahead and take a look at number 24. Okay. Question number 24 is the square root of 128. And this right here is going to be the same thing. So again, the goal for these is to split this into something that is a factor that has a perfect square in it. So it might be a good idea to remind yourself of these. So let's just look and let's write a few of these out. Perfect squares. Okay, perfect squares. 1 is going to be 1. 2 is going to produce 4. 3 is going to be 9. 4 is going to produce, well, let's just, let me write these out. Squared. 16. 5 squared is going to be 25. 6 squared is equal to 36. 7 squared is going to be 49. 8 squared is going to be 64. 9 squared is going to be 81. Okay, and you can kind of see there's more and more that we can continue to write, but I'm just going to do these to start off. 128. So usually I'll try to find something that is divisible by these guys all the way here on the right-hand side. So 128 actually can be written as the square root, in this case, of 64 times 2. Okay, so 64 is a perfect square. It's going to produce 8. So you can actually rewrite it as square root of 64 times the square root of 2. And then when you go ahead and do that, you will get 8 times the square root of 2. And that right there is our final answer. Okay. All right, so you'll notice here that I've got 16 times 8. Now, the thing with that is 16 is a perfect square. So you may say, oh, shoot, I got it. This is going to be the same thing as 16 times square root of 8, which is equal to square root of, or well, yeah, so this is going to be 4, right? Times square root of 8. Now, here's the thing. When you get to this point here, square root of 8 actually has, you can break it down even further. There's more perfect squares that sit inside that 8. So this right here is the same as square root 4 times square root 2, okay? Which is 2 square root 2. So really what this is right here is 4 times 2 times square root 2. Now notice that this and this up here is exactly the same thing. 4 times 2 is 8, and then what's remaining inside is that square root of 2. Okay, so that is something to keep in mind, super important. Simplest form is usually going to bring it down to the point where this right here, the thing that's inside the radical, is just not going to be able to be factored into a perfect square any further. Okay, so that's 24. And let me keep these perfect squares here on the side just as a reference. 26. Now what we're going to do is we're going to look at cubes. So, party time. 54. Cube root of 54. All right, so now instead of looking at perfect squares, we're looking at perfect cubes. I don't expect you to have all of these memorized, but I would think that you should probably have just a couple in the back of your mind for cubes. So let me just write cubes right here. I'm going to erase this here in just a minute because, frankly, it's just not that. Oh, this is cubed. These don't show up a whole lot, but when they do, it's kind of important to know them. 2 cubed is going to be 8. 3 cubed is going to be 27. 4 cubed is going to be 64. 5 cubed is 125. Okay. We'll stop there. I think that's sufficient. Really, you don't need to go any further than that. So usually what I'll do when I see these perfect cubes is I'll try to find something that's smaller, the results. So 27 in this case looks like it could work. And sure enough, in this case, 27, this is the same thing as the cube root of 27 times 2, right? Because 54 divided by 27 is 2, or 27 times 2 is 54. So here, when you go ahead and continue working this out, you have a cube root of 27 times the cube root of 2, sorry. Getting my numbers all mixed up here. Cube root of 2. So this is going to be the same thing as 3, right? Because the cube root of 27 is 3 times the cube root of 2. Okay? And that is our final answer. All right, I'm going to erase these cubes because we don't really need them too much. We're mostly going to be looking at squares. Squares show up a lot, so that's really what our main focus today is going to be. Let's go ahead and look at 37. 37 is saying the square root of 45 x squared. Okay, we're going to start throwing some variables in here. Y cubed, z to the 5th. And this is going to be the... we can actually break this apart even further. So again, 45, let's see if there's anything over here on the right-hand side that could be a factor of 45. 25 won't work, 16 won't work, 9, it looks like 9 will work. So we can have the square root of 9 times 5, right, that's a factor, times the square root of, and I'm just splitting the variables apart here, and I'm going to show you why here in just a second, z to the 5th, okay? So this is the same as square root 9 times square root 5, and let me just do them all separately, x squared, square root y cubed times square root z to the 5th. Okay. When you start to get into the variable components, usually it's a little bit easier because you don't have to do so much factoring. You can really just look at the exponents to determine. So in this case, well, let's just take a look at these numbers first. 5 I can't do anything with. It is as low as it will go, as simplified as it will be. This is going to be 3 times square root of 5. Now, the thing with this is you can take the square root of x squared, and the reason why is because it's the same thing as x times x. So that means that this is going to just produce an x. How do I deal with this is the question. That one's easy. It was a lot simpler. This one's a little trickier. And the way to deal with this is by looking at the factors that sit inside of y cubed. So I've got y squared times y. Similarly here, we could do z to the fourth times z. Y squared and z to the fourth are also perfect squares. Okay? So if I wanted to keep breaking them apart, times x times this guy, y squared, is just going to be y. And then I'm left with square root of y, or radical y, times square root of z to the fourth is z squared. Because z squared times z squared is z to the fourth. And then I multiply by my square root of z. Okay? All right, so we're almost there. What we'll do is the things that are in front of radical signs will stick in front. The things that are under radical signs will combine and merge together into a single radical. So 3x y z squared times the square root of 5 times y times z. So this right here is going to be our final answer. All right, let's go ahead and keep moving on. Let me erase this stuff. Let's do, let's see here. I don't want to do that one. Let's do 55. Okay, these are the ones where we're going to start adding and subtracting, multiplying and dividing. Okay, so we have 3 square root 108 minus 2 root 18 minus 3 root 48. And now what do we have? So let's take a look. 108. Okay, see if there's any of these that are factors. And one tricky way, or one easy way to do it, I would say, one simple way, is you can literally pop it into your calculator. You can say 108 divided by, and then just try a bunch of these values to see if one of them will give you a whole number. And sure enough, I went ahead and did some legwork for you. And I'm going to actually write out all the factors so you can see exactly what they look like. We're going to have 36 times 3 minus 2. 18 is going to be 9 times 2. And 48 is going to be 16 times 4. Oh, times 3, sorry. Wow. Hello. Okay. So you do have these numbers sitting out in front, and then you have the square roots of each. So this is the same as 3 square root 36, square root 3, minus 2 square root 9 times square root 2, minus 3 square root 16, square root 3. Okay, so 3 times square root of 36 is going to be 6, minus 2, 2 times square root of 9 is going to be 3, minus 3 times 4 square root 3. And now we do all the multiplication, okay? This is going to be 18 times square root 3 minus 6 square root 2 minus 12 minus 3 times 4. This is a 4. This is a positive, by the way. That's a multiplication sign. This is going to be 12 square root 3. Now, we are not done yet, okay? Here's the important thing. These numbers, because I have a square root 3 and a square root 3, I can actually combine them. I cannot do anything with that because it has a different radicand. But the 3 here and the 3 here as these radicands, I can merge the coefficients of those values. They're technically not coefficients, I shouldn't say that. they are numbers, I can use the distributive property and combine them and merge them together. So 18 minus 12 is going to be 6 root 3, and then I'm left with a minus 6 root 2. And if you don't have to do it. This is perfectly sufficient answer, but if you want to, you can factor out a 6, and then you would do root 3 minus root 2. Okay, you could do that as well. So, but this is perfectly acceptable, totally fine with that. This is just the extra step. All right, question 55 is done. We are going to move on to question number 68. Okay. And we have 3 root 8x squared y minus 2x root 32 y cubed. Okay? All right, so what we're going to do here is pretty much the same thing we did for the last problems, okay? Break everything apart. Really what we're trying to do is to try to look at these values, these numerical values that are sitting out in front inside those radicands. So here we're going to have 3 times root 8 can be broken up as 4 and 2. So this is going to be 4 times 2 times x squared y minus 2x. 32 can be written as 16 times 2 y cubed. Okay. And if you want, actually I'll do this just to make it a little bit easier to see. Y cubed is the same as y squared times y, right? And y squared, we know that's a perfect square. So it actually makes it a little bit nicer when you work through these. So this is going to be square root 4 times square root 2 times square root x squared times, man, my square root symbols are really struggling right here, y minus 2x times square root 16 times square root 2 times square root y squared times square root y. Okay. So 3 times 2 times square root 2 times x times square root y minus 2x times 4 times square root 2 times square root 2 times y. So you can kind of see I'm doing this progressively, just working one piece out at a time. 6 x times square root 2y, those are both under square roots, minus 2 times 4 is going to be 8x, what are we missing, y times square root 2y, okay? I feel like I missed something. Oh, I did. This is, yeah, okay. Well, whatever. This is supposed to be cubed. My fault. So, y cubed. It's going to be the same as this. Let me just tell you that. All right, so this is going to be y cubed, and then this is going to be y right there. There we go. Okay, now you'll see the radicands are exactly the same. So are the pieces out in front. So we can actually combine this. This is going to be 6xy minus 8xy is going to be minus 2xy times the square root of 2y. Okay? Sorry about that mistake. The big important thing to remember is that when you see a y cubed, or the square root of a higher index, say like there's a higher index on this, or higher exponent, you have to kind of break it apart into something that, in a sense, can be divided by 2 because it's a square root. It's kind of hard to explain. Basically, the number here, you want to try to find or break it into factors that are, one of them is a perfect square. So that's the idea. All right, so that's our final answer, and I will go ahead and erase. Let's look at got a couple more. I'm going to do question 98. We're going to just do multiplication. We basically have been doing multiplication with the adding and subtracting, so these kinds of problems shouldn't be too difficult. Hopefully not. So we have square root of a cubed b times the square root of a b to the fourth. So again, simple procedure. Let's just combine them all together. A cubed times b times a times b to the fourth. Again, when you're adding and subtracting, you can't do that, but when you're multiplying, you can combine them. So this is the same thing as the square root. A to the third times a is going to be a to the fourth. B times b to the fourth is b to the fifth. Okay. And now we can go ahead and break these into their individual perfect squares. So a to the fourth is the same thing as a squared times a squared. Those are perfect squares. A to the fourth technically is a perfect square. It's just a squared. But you'll see something cool happens here in a minute. This is the same thing as, we'll do b to the fourth times b, just so I can prove to you something. Square root of a squared times square root of a squared times square root b to the fourth times square root of b. Okay. Here, these are going to just be a squared, or I should say, these are going to be a. These are going to be, this is going to be b squared, and then this is going to be times root b. Okay, because we can't do anything with that. So here we get a squared, we get b squared, and then we get square root of b. Now, here is the cool thing. Take a look at what happened here to here. Okay? If I take the square root of a squared times the square root of a squared, I get a squared. It's very interesting. Or the square root of a to the fourth is a squared. So that is something to keep in mind. The square root signs, this kind of goes back to the last section, but remember, you can think of square root signs as to the 1/2 power. So if you do that, think about it like this. The square root of a squared is the same thing as a squared to the 1/2, which is the same thing as a to the 2/2, which is equal to a. Okay? So that right there is kind of important because this shows up actually quite a bit, surprisingly, in a lot of different places. But I just wanted to show you that cool little fact. So, all right, let's go ahead and keep going. We've got a couple more questions, and then we're going to call it 173. Hello. This one is going to be where we introduce the idea of a conjugate. Okay, so here we have 2 over root 5 plus 2. Now remember, when you are looking for, kind of going back in time, when you're looking for common denominators, you can multiply by a number, any number times it's divided by itself, right? So if I were looking for a common denominator with 1/3, right, I would multiply whatever I'm looking for times 3 over 3. It's the same idea. So this is kind of the same idea. You're in a sense just using a trick to multiply by 1. But what you can do is essentially remove the denominator, okay? When you go and simplify into simplest form anything that has a radical, it must not have any radical in the denominator. Okay, this is called rationalizing the denominator. Okay, We need to rationalize this. So in order to do this, what we're going to do is multiply by root 5 minus 2 all over root 5 minus 2. Okay? So you'll see this right here, square root of 5 plus 2. This is what's called the conjugate. Okay? It's almost identical. The only thing that's missing or different is the sign that's in between. Now, why am I doing this? Why am I multiplying by a conjugate? Because what happens is, remember what I said in the last question? If I have square root of a times the square root of a, or square root of a squared, how it just gets rid of the square root signs completely. It's the same idea. Okay, so what we're going to do, this is one of those special FOILs with the term being exactly, or basically the terms are the same. The only thing that's different is the sign. This is the same thing as the square root of 5 squared, or square root of 5 squared, minus 2 squared. Okay? And then the top is going to be 2 times radical 5 minus 2. Okay? So when we work this out right here, square root of 5 squared is literally just going to be 5. This is going to be 4. So we're subtracting 4. Now don't say to me, hey, wait, isn't it positive? Because if you do a minus, remember the minus sign is outside of the brackets. If I did inside brackets, it would be positive, but it's not. Okay? I'm subtracting 2 squared. So I'm subtracting 4. This is going to be 2 radical 5. This is going to be 2 radical 5 minus 4. So here we get 2 radical 5 minus 4 all over 1, which is equal to 2 radical 5 minus 4. Okay? And that is our solution. Sweet. All right, moving on. Here we go. Man, my eraser is a mess. One more problem. We're going to do the complex conjugate again, or not the complex, sorry. The conjugate. I'm jumping ahead of myself. In a couple of sections, we'll talk about what a complex conjugate is. Not there yet. Square root 2 plus root 3 all over root 3 minus root 2. This is equal to well, first, actually, what we need to do is multiply by the conjugate. I just said that. So this guy right here is going to multiply by root 3 minus root 2. Okay? This is going to be root 3 minus root 2. Okay? Now, the denominator is relatively straightforward. Let me just tell you what it is really quick. Oop, this is plus, sorry. Plus the opposite signs. Okay. Plus the denominator is going to be pretty easy. Remember, so when you have the opposite signs and the values are the same, this is one of those special foiling cases or special factoring cases. So what's going to happen here is I'm just going to be left with a 3 minus 2. Okay? And if you want to prove it, multiply it all out, add it all up, combine it, you'll get exactly the same thing. Now we have to FOIL the top, okay? So let's do first. This is going to be root 2 times root 3. Outside is going to be root 2 times root 2, which is just 2. Inside, root 3, sorry, this is all plus. Root 3 times root 3 is going to be 3. And the last is going to be root 3 plus, wow, what am I doing? Root 2. There we go. Okay. My real janky fraction right there. Okay. So this is root 3 times root 2 is going to be root 6 plus 2 plus 3 plus root 6. Okay. All over 1. That one's easy. Root 6 and root 6, I can add those together and get 2 root 6. So 2 root 6. 2 plus 3 is going to be 5. And that right there is going to be our final answer. So if that's pretty much it for section 7.2. If anyone has any questions, don't hesitate to let me know. Have a good one.